All right, welcome back. We're here to do passage one, or start with passage one on the first Examkrackers test, and we're anxious to get started, I think. John, you anxious?
I'm ready.
We're going to look first, obviously, in the physical sciences section. Let me say that I hope everything went well the other day when I retook the exam. Our plan is to go through every single question, obviously, in the science sections here, and maybe have a little fun along the way while we're trying to learn something.
MCAT's a fun test.
It is. Let's look at question one. It says, how would the acceleration versus time graph be related to the velocity versus time graph from experiment one? So let's take a look at the diagram that's going to describe the experiment done in, or describe what's done in experiment one. And what we have here is a glider running across an air track. And we need to assume here that this is going to be essentially a frictionless air track. There's not going to be any air resistance working against the glider, and there'll be no friction from its movement across this track. The net force then on the glider is going to be zero. Now what some students do, and they get a little bit confused by this when they look at this, is they assume that the problem, or that this question might also involve the push at the beginning. So let's be real specific here. If I'm a student and I give a push to the glider, once I let go, that's really the time period that we're looking at. That's really the experiment that we're looking at. Once I let go, there's no net force on the glider. If there's no net force on the glider, then of course there shouldn't be any acceleration on the glider, or by definition there won't be any acceleration on the glider. So we could describe an acceleration over time graph as a constant acceleration of zero. There is no acceleration. No net force means no acceleration. And if we're not accelerating, then what happens is, if we're not accelerating because there's no force, then the velocity of the glider over time is also going to be constant in this case. No acceleration, no change in velocity. We're going to have a flat line. I can't tell because they haven't given me a number what exactly this velocity is, but I know that the glider is moving at a constant velocity over time. So let's find the answer choice then that says exactly that. B says the slope of the velocity versus time graph is equal to the instantaneous acceleration. The slope of this line right here is zero, and that would be equal to, as we said, the instantaneous acceleration. So we've got no acceleration, slope of the line is zero. B is the best answer for this question.
Yeah, let me just point out that in question one, you actually didn't have to know anything about the experiment because B is always true. The slope of the velocity versus time graph is always equal to the instantaneous acceleration.
Great. Let's look at question two. Disregarding air resistance and friction, which we should assume which I've assumed to be true already, disregarding those two, which of the following is the correct velocity versus time graph for experiment one? We already really did this problem. We've got a velocity versus time graph with zero slope. Let's find that. Answer choice A. It's the only one that works. Best answer for question two then is A. Question three. Before performing experiment two, the student made a prediction about the form of the velocity versus time and acceleration versus time graphs. Unfortunately, the student neglected to take into account air resistance, and the ball was fairly light. How did the graphs displayed by the computer compare to the prediction of the student? So let's go ahead and take a look at experiment two. This will take both those off. Put experiment two up here. Now we've got a slightly different thing happening. Now we've got a ball dropping towards our SRD. And what's going on is, obviously, as the ball drops, it's being, or as the ball is in space, it's being affected by the force due to gravity. So there's an acceleration on the ball. If it were a lead ball, it would drop and it would accelerate how, John? At what value?
Right, 9.8, and for the MCAT, 10.
10 meters per second squared. This ball would fall fairly rapidly towards the SRD. And if a student if a student assumed that there was no air resistance and that the ball was fairly light, one would assume that any ball then should drop at 10 meters per second squared. But let's assume that this ball is incredibly light. It's light as a feather and it's huge. It's sort of the size of a beach ball. This ball, because it's larger and because it's light, it's going to be affected. Even though it's going to be accelerated towards the ground, it's going to be affected as it bumps into air molecules on the way down. It will be affected by air resistance. So its acceleration due to gravity, because there's a downward force on it, mg, and an upward force here, air resistance, there's going to be a net force on this ball in a downward direction, but it won't be as large as the force due to gravity. In other words, the F equals ma here, the net force down and thus the net acceleration down will be less than the acceleration due to gravity. So let's find the answer choice that's going to say that. C says the computer's velocity versus time graph had a less steep slope at every point. And
remember from number 2 and number 1, the slope of the velocity versus time graph is the acceleration. So if it's less steep, it means less acceleration.
Great. And so let's just...
And so that's the first part is correct.
Okay.
We answer C.
Thanks. And the acceleration versus time graph had a smaller magnitude at every point. So we could draw acceleration versus time graphs here. For this one, in other words, for a lead ball dropping, the acceleration versus time graph would have a fairly steep slope. It would reflect an increase in velocity of 10 meters per second squared.
So the slope would be 10.
Yeah, so the slope here would be 10. Versus, let's really exaggerate this. Let's say that there's a lot of air resistance working against this very light ball. It might have a slope of 1, let's call it. It's going to accelerate much more slowly, and then the velocity that it will attain over time will be much smaller relative to the velocity that this upper ball here, or the lead ball, will attain.
Right. Again here, answer choice C is saying the same thing in the beginning and the end. The slope of the velocity versus time slope is less steep, which means less acceleration, and then the acceleration versus time graph had a smaller magnitude, which means less acceleration. So it's really just restating the same thing twice.
It's a nice question. Good. Question 4. In calculating the distance from the SRD to an object, the computer program assumes the speed of sound is 343 meters per second. Suppose that on a given day the speed of sound is actually 332 meters per second. How would this affect the results of experiment 1? So let's go ahead and throw experiment 1 back up there. And this is an interesting question, and one in my mind that lends itself to some exaggeration. What's going on is, obviously, a SRD, or a sonic ranging device, the function of this thing is to measure the speed at which the glider is moving. And what it does is it sends out a sound wave. The glider's moving. The SRD sends out a sound wave. It hits the glider and comes back. The SRD sends out another sound wave, and it reflects and comes back. The computer in the SRD measures the distance between the two findings of the glider, and it calculates a velocity for the glider.
Right, and that distance is based upon the time difference between how long it took the first sound and the second sound to come back.
Right. So what's going on here, and what this question is asking about, is if the sound wave didn't move as fast as we thought it would. So I'm going to portray a sound wave, right? If I'm a sound wave coming from the SRD, here's the glider, right? If I'm going what I expect, or if I'm going what the computer expects me to go, I tap the glider, I come back, I tap the glider, and I come back. I'm moving fairly quickly back and forth. I can measure the distance that the glider travels between those two measurements is going to be fairly small. Everything's going to work fine. But if I go a little slower than that, now here's me as a sound wave moving a little slower, and see how I'm exaggerating the example. Oh, I wish I could catch up to that thing. Hit. Now I got to turn around and come back. And the problem is, as I'm moving slowly here, the glider is moving further and further away. The computer is expecting these two pulses to come back very quickly. I'm going to now go after the glider again, get all the way over there, tap it, come all the way back like this. I'm going to mess up the computer. What's going to happen?
So it took you a long time, and the computer doesn't realize you're moving slowly. The computer thinks you're moving fast.
Fast. So the computer assumes now that in the time period, the glider has gone much, much further. So it's assumed. So the assumption the computer is making is bad. Let's find the answer choice that says that. B says the calculated velocity will be greater than the actual velocity. What's going to happen is the computer is going to think that the glider went much, much further in a given amount of time. It's going to screw up the data for the experiment. Best answer for 4 is B.
Right. Notice we could get rid of this or narrow down 2 answer choices. Answer choice C and D, because the calculated acceleration will be less than the actual acceleration. There's no acceleration here. So it's calculating velocity. So you should at least have narrowed that down to A and B.
Great. Question 5. Adjusting for air resistance, approximately how much time is required for the ball to reach the ground in experiment 2? So I'm going to throw up again experiment 2, and I want you to note that one of the things MCAT will do to us is it'll flip back and forth between experiments. In other words, we had 2 experiments in this particular passage. One question was about experiment 1, then we went to experiment 2, we went back to experiment 1, and now we're back to experiment 2. And that's completely intentional. It's designed to sort of throw you off your game a little bit, if you'll forgive the expression. So now we've got the ball dropping, and we're going to adjust for air resistance. And essentially, any time a ball drops, we've got a projectile motion problem, or in this case, a free fall problem,
Now this is true, but before you go into the calculations, notice there's no reason to do calculations on this question.
Excellent.
Answer choice A, B, and C all have the square root of 0.2. One is less, one is exactly that, and one is more.
Okay.
So why would they have 0.2? What must that be?
That must be the amount of time.
The amount of time without air resistance.
Okay.
Right? And then the question asks, adjusting for air resistance. What does air resistance do? It's going to slow it down, right? So if it slows the ball down as it drops, should it take more time or less time?
Awesome. It should take more time.
Right. So we're looking at answer choice C.
C. Best answer for 5 is C. Just in case you wanted to do it formulaically or you started to set the formula up, it would come out of the free fall equation or out of a linear motion equation. D is equal to D naught plus V naught T plus 1/2 AT squared. There's no initial velocity of the ball and no initial displacement. So setting these two equal and doing some algebra, we can get that T is equal to the square root of 2D over A. From the passage, it tells us that this height, this distance here is 10 centimeters. So it's 2 times 0.1 over 10. We'd have this, I'm sorry, it's 1 meter is the distance that the ball falls. So it's 2 times 1, or 2 over 10, 0.2, square root of 0.2. It would be more, that would be the time, if this ball is not affected by air resistance, that would be the time to fall. It's now more than that. So, and the only reason I wanted to go through this is twofold. Obviously, to do it the simple way is the way John's doing it, the better way to do it here. But if you did set up the math, it's just another way to solve the problem. And I do think it's really important that you know this formula going into MCAT, and it's going to affect any object falling from zero initial vertical velocity.
Okay, we're on passage 2. In passage 2, we have this setup where we have water here and these 2 electrodes stuck into the water, and then this is plugged in to presumably a 220 volt socket or some kind of socket here, and then a light bulb here. Now, in order for the light bulb to light, we have to have, the circuit has to be complete. So we have to have electricity going from one electrode to the other and around through the light bulb and back around. So we have a complete circuit. And what's going to break that circuit is if the solution does not conduct electricity. When there's pure water, is there going to be electricity conducted through here?
There will not be. There's no electrolytes in pure water.
Exactly. There are very few electrolytes. There's 10 to the negative 7th hydrogen ions and 10 to the negative 7th OH minus ions. So there's 2 times 10 to the negative 7th total ions in pure water. Not enough really to conduct a nice current and light the light bulb. But once we dump in some barium hydroxide is going to break into
barium and hydroxide ions.
Barium 2 plus and some hydroxide ions, and that's going to conduct electricity and cause our light bulb to light up. And that's what's happening in experiment 1. Now let's take a look at question number 6. From the results of experiment 1, the color of phenolphthalein most likely changes from, and here the best answer is C, colorless to pink when going from pH of 7.8 to 9.8. What they've done is they kind of went backwards. The solution starts out pink with a lot of barium hydroxide because barium hydroxide has a high pH. So when it's above 9.8, we have a pink solution. And then as we add and what are we adding? Our H2SO4.
An acid.
Exactly. We neutralize it. We bring it down to a pH towards 7. But before it gets to a pH of 7, before the light bulb goes out, we have the phenolphthalein turns to clear or colorless. So that's how we get C, colorless, when going from pH 7.8 to 9.8. Okay, the question just gives it, the answer choice gives it backwards, 7.8 to 9.8. We're thinking about it from 9.8 to 7.8.
So at the lower pH, the solution is colorless, and at the higher pH, 9.8, the solution is pink, and that's because of the base that's in there. So
exactly, and we know it's above 7 where it changes from experiment 1. Okay, so A and B have to be wrong. Question 7. What is the concentration of hydroxide ions in the barium hydroxide solution in experiment 1 before H2SO4 is added? The KSP for barium hydroxide is 4 times 10 to the negative 3rd. All right, this is just simply a simple saturation solution problem. They give us a KSP and they tell us that the barium hydroxide solution is saturated, which means we've dissolved all the barium hydroxide that we possibly can. So when the equation that we're going to be thinking about is barium hydroxide plus water is going to go to barium 2 plus 2 OH minus. And then we're going to take our, let's imagine our solution. We dump X amount of moles into here. We set up the KSP. KSP equals the barium concentration times the OH minus concentration squared. This 2 goes here. Now I'm not going to use barium hydroxide here. Why not?
Because we're talking about the solubility product and as a pure solid.
Pure solid, we don't use it in the equilibrium constant. Okay, now we need to know what is the concentration of barium. Now if we're dumping in barium hydroxide here, for simplicity's sake, let's imagine we have a liter of solution and we dump in X moles of barium hydroxide and dissolve X moles before it gets saturated. That would give us X moles of barium per 1 liter. If we just started with a 1 liter solution, which is the simplest way to do it. So our concentration of barium 2 plus is X. What's going to be our concentration of OH minus?
2X.
Right, because we have, for every barium, we get 2 OH minuses. So our concentration will be 2X here. So I'll put in 2X, and I have to square it here. And then I end up with 4X cubed equals 4 times 10 to the negative third.
Because they're giving us the KSP in this question.
Exactly, they gave us as 4 times 10 to the negative third. The 4's drop out, X cubed equals 10 to the negative third, so X equals 10 to the negative 1. Now what was the X?
X is the number of barium ions or the number of hydroxide ions.
It's the number of barium ions, but it's half the number of hydroxide ions. So we have to multiply this by 2 to get the total number. Because remember, the number of hydroxide ions was 2X, the concentration. So answer choice is 2 times 10 to the negative 1, choice D. Question number 8. Why isn't light emitted from the light bulb when the copper leads are placed into distilled water? Answer, we already answered that. Sure. That's choice A. Pure water is a poor conductor of electricity. Why does the light remain on throughout experiment 2 but dim during experiment 1? Okay. In experiment 2, as we add barium hydroxide, as we add the H2SO4, the H will react with OH minus to make water, right? H plus is going to react with the OH minus, and we get water. That's going to neutralize the solution. But then there is the sulfate ion. So we get barium sulfate. And the barium sulfate is actually the white precipitate that comes out in experiment 1.
So all this is happening in experiment 1. The reason that the light dims in experiment 1 is because the barium sulfate, those two ions you should recognize as not very soluble. What happens is they form a precipitate. They connect together and they precipitate out of solution. So we lose electrolytes from solution. The light bulb dims.
Exactly. And actually, you don't even have to recognize barium sulfate as insoluble because they tell you a cloudy white precipitate forms. What could it be? It's got to be, if we're adding H2SO4 and barium sulfate, we know that the H plus and the OH minus is going to make water. What's left over? Barium and sulfate. So it's got to be the barium sulfate. When the barium sulfate bonds together and precipitates, we're left with pure water. So that's why the light's going to dim. Now in experiment 1, what are we adding? We have HCl. Experiment 2, we have HCl and NaOH. And NaOH gives us Na plus and OH minus. HCl gives us H plus and Cl minus. Again, these two make water, but sodium and chlorine do not precipitate, right? You want to know they're very soluble. So they conduct electricity. They remain electrolytes in solution, and so the light stays on because they conduct electricity. So best answer choice for number 9 is D. Electrolytes are removed from solution by the reaction in experiment 1, and electrolytes are created by the reaction in experiment 2. Question 10. If the initial solutions in both experiments have the same pH, which solution has the lowest vapor pressure? This is a very tough question. What we want to look at is, in terms of vapor pressure, if this is a solution and we're looking down on the top of a solution, and you've got these molecules here of your solution, let's say actually let's call it a pure liquid. And these are the molecules at the surface of this pure liquid. We're looking down on top of a glass. These molecules, some of these are moving fast enough to escape. If I put my hand over that, they collide with my hand, and that's the vapor pressure. The force against my hand divided by the area is actually a measure of the vapor pressure. So I have a lot of molecules here, and say 1 out of 10 is escaping, right? That depends on what the temperature, right? And so as the temperature increases, the molecules move faster and more molecules escape. So that's my vapor pressure. Now, if I add a non-volatile solute, non-volatile means?
No vapor pressure.
No vapor pressure. There's no escaping molecules. If I add a non-volatile solute, and let's say it's a mole fraction of 0.1, in other words, 1 out of every 10 molecules is non-volatile solute, those non-volatile solutes take up some of the space, and they cause fewer of the volatile molecules to reach the surface and be allowed to escape. So I actually lower the vapor pressure when I have these non-volatile molecules. Okay, so when I compare the two solutions, barium hydroxide and sodium hydroxide, I see that to get the same number of hydroxide ions, I actually have to add twice as much sodium hydroxide, right? Because for every barium that I add, I get 2 hydroxides. For every sodium I add, I get 1 hydroxide. So here that makes the best answer choice D, the sodium hydroxide solution in experiment 2, because it contains more metal ions. And the metal, of course, we're talking about is the sodium or the barium. So the solution with the lowest vapor pressure, when the pH is the same, that's actually key. I kind of skipped that. The pH is the same. What does that mean if the pH is the same?
If the pH is the same, that means we have the same number of H plus ions or the same number of hydroxide ions in solution. And because for every one of these, we're going to get 2 hydroxide ions, and for every one of these, we're going to get only 1, we have to put twice as much sodium hydroxide as barium hydroxide in solution to get the same number of hydroxide ions from this compound. So essentially, we're going to have twice as much sodium as barium.
Exactly. Okay. All right, and so if we have twice as much sodium, that's twice as many non-volatile solute molecules, which means a lower vapor pressure.
And of course, the sodium is the metal there, so that's why the phraseology of answer choice D is done that way.
Answer choice D then for number 10. Question 11. What is the identity of the precipitate in experiment 1? We covered this as barium sulfate because we know the protons react with the hydroxide to make water. What's left? SO4 2- and barium 2+, and those, of course, will combine to make the precipitate. So answer choice B for 11. Question 12. In experiment 2, why does the intensity of the light bulb stop increasing? Okay, so the intensity of the light bulb here is going to increase in experiment 2, but at some point it reaches a maximum. And it's going to reach a maximum because the solution becomes as conductive as it's going to become. In other words, it's conducting as much current as it can conduct. So there are really 2 possible answers at first glance, C and D. C is the solution reaches a point of maximum conductivity, where additional ions will no longer increase the current between the copper leads. That's the correct answer. D, you might look at and think is correct at first. The solution reaches a point of maximum conductivity where additional ions will no longer increase the voltage across the copper leads. But let's take a look at that. What defines this voltage across here?
The power source.
Exactly, the plug here. We plug it into a voltage source, and that defines the voltage across here. So the voltage is already defined, and from Ohm's law, V equals IR. What's changing is we add a solution to this. We add ions. The resistance changes. It goes down, and the current goes up. At some point, we get a minimum resistance and a maximum current, or else a maximum conductivity and a maximum current. So answer choice C is the best answer for 12.
And just so we hit A and B very quickly, the sodium chloride solution doesn't become saturated. We should know that sodium and chloride are very soluble ions, and there's no indication in experiment 2 that we actually get a precipitate. So we shouldn't make that assumption on the MCAT. So if you made that assumption, bad assumption.
Right. Sodium chloride is, you're not going to have a saturated solution of sodium chloride on the MCAT. It's very soluble.
All right, we're looking at passage 3. Passage 3 begins with question 13. The method described in this passage was not the method used historically to make the first estimate of Avogadro's number. Instead, the well-known value of the charge on a mole of electrons, 1 Faraday, was used. In addition to this value, what other information had to be known to determine the value for Avogadro's number? So we're looking for Avogadro's number, which of course is the number of anythings in a mole. And the value that we're given in the question is 96,500. This is Faraday's number. Probably not a bad number to put in your memory bank somewhere as the number of coulombs per mole of electron. So what we've got here is a charge per mole of electrons. And it says, the question asks, what other value would we need in addition to this one to be able to calculate Avogadro's number?
And Avogadro's number then is the number of something per mole.
Yeah. That's what I said. Okay. Cool. So 96,500 coulombs per mole of electrons. If we knew the charge on an individual electron, we could divide this by that and we could calculate Avogadro's number. So let's see if that one's here. Oh, there's Roman numeral 2 says the charge of one electron. That's got to be a truism. So A has got to be wrong because it doesn't include 2, and C has got to be wrong. We're down to B and D. We can eliminate answer choice D because the mass of one electron, well, given this information, really that's not going to be useful to us in calculating Avogadro's number. Again, this is coulombs per mole of electrons. If we knew the charge on one electron, we could pretty easily calculate Avogadro's number. John, just for argument's sake, what is Avogadro's number? Because I forgot.
6.022 times 10 to the 23rd.
Times 10 to the 23rd. Again, this number and this number, I'd probably commit them to memory. Great. Question 14. According to Vesper theory, what is the shape of SO2? So we might consult our periodic table, and you should know that S is a chalcogen, appears immediately below oxygen, and from that you should be able to draw the Lewis dot structure for SO2. We need a valence set of 8 around each of our atoms, which means that the S here, because it's doubly bound here and singly bound here, has got to have its lone pair, making this a bent shape. Let's find the answer choice that says that. Answer choice A says bent. 14 is A. 15, probably the hardest question of the group or of the bunch. It says, if the watch glass has a diameter of 20 centimeters and the volume of the acid solution added is 0.1 milliliter, which of the following represents the approximate thickness of the monolayer in centimeters? And what I want to do is I want to look at the diagram that they've given us in this passage, which I've drawn or approximated up here on the board. What we're looking to do here is we're looking to take a volume of solution containing this arachidonic acid. We're looking to pour it across a dish, and we're looking to form a monolayer. In other words, a layer one molecule thick, right? And we want that evenly spread over the surface of this dish. So what we have now is we have a volume, or the unit of a volume would be a meter cubed, right? Spread over the area of a dish, which would be area, and the unit of area obviously is meters squared. If we put meters cubed over meters squared, we're going to end up with meters, and that would be the thickness of the monolayer. Well, in centimeters, but we could do the same. This could be centimeters cubed and centimeters squared and give us the same value. Now, interestingly, once you see the signs, now this looks at its surface like it's really hard science. Once you see the signs, you understand how to set it up. Notice that only answer choice B has in the denominator has a value for the area of a circle, right? And the area of a circle, of course, is pi r squared. It's the only answer choice in there that would indicate, that would give us area. All the others we can eliminate because they don't indicate area. I mean, none of the others even include pi. Best answer here for 15 then must be B.
Right. Now, the way I look at this problem is I look at because I hate these answer choices where they have numbers and not variables. And I'll look at this problem and I'll see, well, I don't want to do all the science here. I wonder if I can use units. 3.14 is in each answer choice except D. Clearly 3.14 is pi. The units of pi are no units at all. 10 squared then is going to be my radius squared. And again, I recognize that as area then, pi r squared. So I know the denominator of D is square meters. And I'm looking for an answer choice in meters. Notice none of the other answer choices are in meters. In the numerator, they've got 0.1, and 0.1 is in milliliters. Also, milliliters could be a cubic centimeter. You should know that 1 milliliter is 1 cubic centimeter. And then 0.0001, you should recognize from the last sentence in the paragraph, 0.01% is 0.0001. Again, no units on a percent. So I end up with cubic centimeters over square centimeters or centimeters. B is the only one that has the right units. So it's just a different approach to the same problem.
Sure. And I think the point that John and I are both making is that you stand a good likelihood of seeing a problem on your MCAT that looks exactly like this. In other words, they're going to give you answer choices with only numbers. And at first blush, it's very intimidating looking. And what you really got to do is get in there, and it's really about either using units to analyze it or just figuring out either the denominator or the numerator of the fraction. And it usually almost solves itself at that point.
Yeah.
Great. Question 16 says, what type of bond forms between the carboxylate group and the water? Now, of course, the carboxylate group is indicated in my diagram by the circle here at the bottom of the fatty acid. And the carboxylate group, of course, C double bond O, OH. We've got a hydrogen here that can hydrogen bond. It will hydrogen bond with the water. Let's find the answer choice that says that. That would be C, hydrogen bonding. Of course, covalent and ionic bonding there you should have eliminated because we're not forming any intramolecular bonds here. These are intermolecular bonds. Best answer here would be hydrogen bonds.
You know you're not forming an intramolecular bond because that would create a new chemical. Right? These are physical bonds, so it's hydrogen. And what type of bond? What's a Lewis bond anyway?
Yeah.
We can skip that one. Okay.
All right. Question 17 says, what is the conjugate base of arachidonic acid? Arachidonic acid, yikes. That's like involving spiders, right? Arachidonic, in the second paragraph, it says arachidonic acid, an unsaturated fatty acid with a molecular formula C20, H32, O2. And it says, obviously, it's an acid. And this question is, what is the conjugate base of arachidonic acid? And of course, if you go from the acid to its conjugate base, you need to remove one proton from it. So we take a proton away, that would make this H31. And if we take a proton with its positive charge away, we'd give it a negative charge net on the molecule. This is our conjugate base by definition. That would be answer choice D, C20, H31, O2, negative. Question 18, why does arachidonic acid float on water but dissolve in benzene? So we're looking for an answer that would indicate to us why this arachidonic acid molecule is going to float on water. Answer choice B says the molecule is nonpolar and is therefore more soluble in benzene. So of course it's going to dissolve in benzene because it's nonpolar. B is the best answer here. But what's weird about A and C in this case is that they seem to be right. I mean, they seem to have some degree of rightness to them.
Right. Now let's just look at B back for a second. I just want to clarify. It dissolves in benzene, but it's immiscible in water. So it's like pouring oil on water. You have two separate layers. And so one layer is going to float on the other. So B is absolutely clear. Best answer, and you should pick it.
Great.
But you're correct. If we take a look at C. Arachidonic acid is less dense than water, but about the same density as benzene. And right here, since it's immiscible, it doesn't matter what the density is. One's going to float on the other. If they're miscible, then it doesn't matter what the density is because they totally mix. So one doesn't float on the other. So here, miscibility is more important than density.
And that's in the wording of the question because clearly it says dissolve in benzene.
Good.
Great. 19. Which of the following, if true, would introduce the least error into the experiment? In other words, and what we're looking for here is anything that would make an error is wrong. Anything that would introduce error into this experiment in this question is wrong. So answer choice A says not all the benzene evaporated. Well, that would be a big error if not all the benzene evaporated. We need to get that out because if we assume that fluid, extra fluid is arachidonic acid and it's in fact benzene, that would
we got a thicker, yeah, we measure it as a thicker disc on top of the water and we mess up our experiment.
So that's clearly wrong. B says surface tension caused the arachidonic acid to form a layer more than one molecule thick before spreading out over the water's surface. What would happen there is we might just get here's our disk, and we might get a globule a couple of layers thick. Clearly we want one monolayer across the entire disk. This would introduce error into the experiment. So answer choice B has to be wrong as well. C says some of the arachidonic acid protonated the water, meaning the carboxylate group or the carboxylic acid functionality that we have at the head end here of the fatty acid loses a proton and becomes carboxylate. And absolutely, this is going to happen. I mean, I would assume this is going to happen quite a bit in our monolayer. So this is going to happen, wouldn't introduce any error into the experiment. D says the arachidonic acid was found to form circular coils rather than vertical columns under the conditions of the experiment. Now here I've drawn with the tails all facing pretty much straight up, but you could imagine a circumstance where if it formed a circular coil, we'd have one little arachidonic acid molecule in the middle here, and instead of having straight up tails, it forms this big circular coil where something strange is going on. It won't let its neighbors in as close, so we won't be able to form that monolayer. That would certainly introduce some error into the experiment. D must be wrong. C must be the best answer.
Okay, passage 4. Now, Jordan's actually on location for this passage, and we'll be contacting him later. So let's do the first few questions first without him. Question 20. According to figure 1, high tide travels along the surface of the Earth from, and the passage explained to us that actually the moon is creating the high tides, and it's the pull of the moon. On the one side, the moon is pulling hard, stretching out the Earth, and on the other side, it's not pulling hard at all, allowing the spinning of the Earth to force this side out. So we have a high tide here and a high tide here. Now the Earth is spinning. And if we imagine this thing, it's probably easiest to first think about the sun. The sun is in place and the Earth spins. And it looks to us on the Earth like the sun is moving from where to where? Rises in the east and sets in the west. So it looks like the sun is rising in the east and setting in the west. Now let's imagine that's the moon, because it's really the same kind of thing. The Earth is spinning and the moon is pretty close to stationary compared to the spin of the Earth. So if the moon's there, underneath the moon is a high tide. As the Earth spins this way, we see the moon rising, and it looks like the moon is moving towards us from east to west because of the spin of the Earth. And underneath that moving moon is the tide coming from east to west. So the best answer choice here is A, from east to west. Question 21. In 11 million years, the moon will be 3,000 kilometers farther from the Earth. How will this affect high tides? Well, the high tide is affected by this equation, Newton's law of gravity, Gmm over r squared. That's an m there. And the difference then in 11 million years, the difference is r is going to be greater. As r goes up, f goes down. And if f goes down, it means the tides are not as great. And you can think of it eventually as the moon's gone, and now we have no high tide because the moon is necessary for the high tide. So best answer choice here is C, the tides will be lower. Question 22. Which of the following planets would not possess at least one tidal cycle? Now what did we just say? We said that in order to have the high tide, we have to have a satellite. So we have to have at least one moon. So if we take a look, a planet that rotates about its axis but does not have a moon, one is incorrect. It will not possess one will not possess the high tide. So one actually is a correct answer. We want a Roman numeral 1 in there. That makes it either A or D. So let's check, looking at the answer choices, right? A is 1 only, D is 1 and 3. So let's just check. We don't even have to worry about 2. Let's check Roman numeral 3, see if that's right. A planet that does not have a moon and does not rotate about its axis. Well, forget about rotation. If it doesn't have a moon, it doesn't have a high tide. So 1 and 3 are correct. Answer choice D is the right answer. Question 23. The gravitational force of the sun on the Earth is 180 times greater than the gravitational force of the moon on the Earth. But the effect of the sun on the ocean tides is much smaller. This is most likely because this is a difficult question. If we take a look at the explanation, here's the moon and here's the Earth. Look at the R's. This R1 and R2. R2 is much greater than R1. There's a significant difference between R2 and R1. Although that difference is the same when we look at the sun compared to the Earth, if we compare the length, this distance here compared to this distance, that distance proportionally becomes very small. So the high tides are given by this formula right here, the difference in the force, and with a little algebra we see it's 1 over r1 squared minus 1 over r2 squared. And if r1 and r2 are very close together, what do we have? Basically this term becomes 0 with 0 force. And that's what happens with the sun. R1 and R2 are pretty close together. Let me put some numbers in there to make it clear. Let's say this is 10,000 and this is 9,999. So the difference is 1 out of 10,000. Very small difference, really, compared to the total difference. Over here, let's call this, the big one, let's call 100, and the little one we'll call 50. So the difference is 50 over 100, or 1/2. Much bigger number than 1 over 10,000. So brings that force way up. So let's find the answer choice that says that, and that's choice B. The diameter of the Earth is small compared to the distance between the Earth and the Sun, but it is large compared to the distance between the Earth and the Moon. So what we might look at this question, because it's so difficult, and try and get rid of 3 answer choices instead of pick the right answer choices. Sometimes that's easier. So let's take a look at A. The Sun is not spinning on its axis. That really doesn't have anything to do with anything. We don't even know if it's spinning on its axis, or for the MCAT, we don't have to know that. So A is out. A's got to be a wrong answer. C, the Moon revolves more rapidly around the Earth than the Earth revolves around the Sun. That's not true. The Earth is moving very fast around the Sun compared to the rate at which the Moon is moving around the Earth. And D, the Sun-Earth system does not contain a barycenter. It describes in the passage what a barycenter is. It's just a center of gravity for the Earth-Moon system or the Sun-Moon system. And of course, the Sun-Earth system does contain a barycenter. There is a center of gravity in that system. So D would have to be false too. So it might be easier to get rid of A, C, and D than to choose the right answer in this one. Remember, there's always more than one way to check an MCAT question. Okay, we're on question 24. At a factory at the North Pole and a factory at the equator, 60 500-kilogram crates must be lifted onto a ledge 2 meters high. According to the information in the passage, if both factories use the same machine operating at maximum power, compared to the machine at the equator, the machine at the North Pole will. Now notice the answer choices right away. They have no numbers. So this is not quantitative. The 500, the 2 meters, this is all done just as red herrings, just to throw us off. So we're going to ignore that. What they're asking here is, when the Earth spins, you want to know that it kind of flattens out. And so R to the North Pole is going to be smaller than R to the equator. And if you recall that from Newton's law of gravity, F equals gmm over R squared. If I want to find out about the acceleration here versus the acceleration at the North Pole, divide by m on each side, and I'm going to get acceleration. So acceleration is gm over R squared, and this acceleration is, we'll call it the g, the gravitational constant. Okay, so we can see here that as R increases, g goes down. So g here is going to be smaller than g at the North Pole. Okay, now let's keep that in mind when we do this problem. We have work equals mgh and power equals work over time. So let's substitute mgh for work over here, and we have mgh over time. So we have power equals mgh over time. Now, they said the machines are the same. They have the same maximum power, so that's a constant. The number of crates is the mass of the crates. That's a constant. The height is 2 meters. It's constant for both places. So what's going to change is time and g. We know that at the North Pole, g is bigger, so at the North Pole, time must also be bigger. Okay? If g is bigger, then work is larger. So looking at the answer choices, which are concerned with work and time, we see that work is bigger and time is greater at the North Pole. So that would be answer choice B, would require more time and do more work. Now we've got Jordan on location at the North Pole. Let's just give him a quick call and we will verify this.
Hello?
Jordan, is that you?
Yeah, I'm on location at the North Pole.
Oh, great. Okay. Hey, we want to verify. We just did question 24, and we want to verify that it actually does take more time and more work is done for the same job at the North Pole. Is that correct?
Yeah.
Hey, that's excellent. I really appreciate it, Jordan. Now hurry back home, all right?
Hey, John, I thought I was going to the equator.
Oh, yeah. Hey, I forgot to tell you, we got cheaper plane tickets to the North Pole, so, I should be happy we saved some money. So hurry back for the next passage.
Okay.
Bye-bye now. What a guy. Okay, let's go to question 25. According to the information in the passage, which of the following could be the acceleration of a body in free fall near the surface of the Earth at the equator? Okay, let's go back to our diagram here. Near the surface of the Earth at the equator, g is smaller than up here at the North Pole. So in other words, at the equator, g is going to be the smallest. Now it's said in the passage that the average for g is going to be 9.81. So the average over this whole surface area of the Earth is 9.81. And we know that the equator is going to be smaller than the average. North Pole is larger than the average. If we take a look at our answer choices, the only answer smaller than the average is answer choice A, 9.77. So A is correct for number 25.
Wow. I'll tell you, John, commercial air travel today, they move quick.
That was fast.
It was. We ready for the next passage?
We're ready.
Let's go. All right, we're up to the first set of freestanding questions, starting with question 26. It says, a piston is used to apply pressure to an ideal gas inside a cylinder. The gas is warmed from 0 degrees Celsius to 25 degrees Celsius at a constant volume of 10 liters. The pressure inside the cylinder increases by 1 atmosphere. How much work is done on the gas? All right, so we're looking really at PV work. And the key really to understanding PV work, or one of the keys, is that if you have no change in volume, which is what it says very clearly in the second sentence in this question, no change in volume means that you don't have any PV work. Because the formula for PV work here would be P, pressure, times the change in volume. If the change in volume is nothing or 0, that would mean the work is 0, making answer choice A, 0 joules, the best answer for question 26.
Whenever I see a 0 as an answer choice, I'll always look at it and ask myself, why isn't it 0? Because they don't put 0 there that often.
That's true, they don't.
And when 0's there, it's usually easy to get rid of if it's wrong.
Right.
So here you'd say, why isn't it 0? And then you realize, wait a minute, volume isn't changing. Oh, it is 0. No calculation. Boom. We're ready.
Good. Question 27. The electron configuration of copper is, so let's just go ahead and look at copper, find it on our periodic table. And there's copper right here in the middle of the 3D orbitals, in the middle of the elements that represent the 3D orbitals. And of course, we just count up the number of electrons here. Copper's going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 after we see the argon gas. So we can eliminate answer choices C and D because they're starting with krypton and adding to that, and then copper would not be there. So C and D have to be wrong. Then it's just a question of, is it B or is it A? Of course, it has to be A because we have 11 and not 12 electrons in this, in copper, in its valence. So the best answer for 27 is A.
Right, and notice I didn't give you the choice 4s2 3d9.
Right.
And they're extremely unlikely to give you that choice because it's MCAT, and they want you to know basic science, not memorize which one of the transition metals has a strange electron configuration. That doesn't mean they won't use the strange electron configuration because they used it here, but they'll make it simple. They'll give you only those possible choices. So choice A here.
Gotta be. Question 28. An ideal fluid moves to the right in a cylindrical pipe shown. The radius of the pipe at point A is 5 centimeters. So here's my pipe. I've drawn the image here. We've got a 5 centimeter radius here, and then we double the radius of the pipe when we go to area B. So the question says, if the velocity of the fluid, and the fluid is flowing to the right, if the velocity of the fluid is 36 meters per second at point A, 36 meters per second in that direction, what is the velocity of the fluid at point B? Now what's going on here is there's a couple of formulas that you have to know and relate to this. The first formula is Q sub A in an ideal fluid flowing. Q sub A equals Q sub B. In other words, fluid flow in region A equals fluid flow in region B. That's must-know information.
And that's just another way to say that volume flow rate is constant in an ideal fluid.
Beautiful. And what that also means is that A sub A, the area of pipe A, times the velocity in A is equal to area sub B times velocity sub B. And that comes from our formula we have to know, which is Q fluid flow is equal to area times velocity. So we got area of A times velocity of A is equal to area of B times velocity of B. And these are cylindrical pipes. So now what we can do is we can plug in for area the formula for a cylindrical pipe, which would be, of course, a circle. That would be pi times R squared times V of A equals pi times R squared of B times V sub B. And what we should see here is that as we double the radius here, these two things are constant, right? So this radius is half of this radius. This velocity then must be 4 times as great as this velocity, because as we double this, the effect of that doubling is going to be squared. The radius, the function of this value in this formula, is going to go up 4 times. These two are constant. This velocity must be 1/4 this velocity, because 4 times 1/4 is 1. This one is 36. This one is 1/4 that velocity. This velocity must be 9 meters per second, same direction.
Choice B.
Best answer. We're up to question 29.
Jordan, can I do this one? I love circuits.
Okay.
Let me do circuits.
You got
All
it, John.
Question 29. If points A and B are connected by a 2 ohm resistor, the power dissipated by the circuit will, and you know me, what I'm going to do is go on and read the answer choices first. Decrease because the current generated by the battery will, so they want to know about the current and the power here, and then if I look at C and D, they also want to know about the resistance. So I'm going to take a look, and I'm going to see what I need to use here in terms of equations. I know, what's the equation for power for a circuit?
P is equal to IV.
P equals IV. And what is the equation for then, I want voltage and resistance in here, because they also ask about resistance. V
equals
law,
IR.
right? Mm-hmm. V equals IR. Okay. Now, when I add a resistor in series, when I put a resistor here, it's going to be in series with this resistor. Let's ignore this here. The current's going to come this way. I'm sorry, thank you. It's going to be in parallel. The current's going to come this way, and it's going to divide like that. Now, whenever I add a resistor in parallel, this is like, resistors are like bridges. If I've got a bridge and traffic is backed up, and I put a bridge right next to it, it relieves that congestion of traffic. Some of the traffic goes over the other bridge. So in other words, it lowers the resistance to traffic. So when I add a resistor here, I'm going to lower the resistance. Look what I'm doing with the voltage, though. On the overall, the voltage stays the same. So when I add a resistor, I lower the resistance. What happens to the current?
Has to go up.
Exactly. The current is going to go up. So I know now that the current, when I add the resistor, current goes up. So for the second part, current is increasing. Now over here we said the voltage stays the same, current goes up. What happens to the power?
Has to go up.
Power is going to increase as well. Let's see if we have an answer choice that says that.
C says exactly that.
Increase because the current generated by the resistor will increase. Right, so the power will increase because the current generated by the battery will increase.
Great.
Okay, we're doing passage 5, question 30. Now, before I go to question 30, let's just look at this experiment. Let's look at what they're trying to do here. And basically, they're trying to derive the ideal gas law constants. Okay? And they're going to do that by measuring pressure, volume, number of moles, and temperature, and then calculating for R. All right, how do they find pressure? Pressure is going to be the room pressure. Volume, they run this chemical reaction, and they're pumping oxygen gas into this flask, and it's displacing a fluid, in this case water, into this beaker. They measure this beaker, they'll weigh the beaker and use density to find the volume of fluid displaced, which will be equal to the volume of gas produced. So that's how they measure the volume of the gas. Number of moles they get from the stoichiometry of the reaction, and that is the reaction given in the equation, the potassium chlorate reaction. And then T is the temperature, and that's just going to be room temperature. Okay, so they measure those variables, calculate for R. Question 30. Which of the following measured values from the experiment does the student use to calculate the volume of oxygen gas in the flask? So remember, as the oxygen gas pushes out or displaces the water up through here and into the beaker, they take the beaker and they weigh the beaker, and then they're going to use density of water to calculate the volume displaced. Now, I don't know why they don't just read the volume on the beaker, but they're going to weigh it. So best answer here is A, the weight of the water. Question 31. The purpose of MnO2 is to, and if we look at the reaction here, in the passage, we see that MnO2 is written above the arrow with heat. It is neither a reactant nor a product. So what is its likely role?
It's probably a catalyst.
Exactly. That's what you're looking at. Now, just because it's above the arrow doesn't mean it's a catalyst. You have to look and see, is it a reactant or a product? Does it do anything to the reaction? And all it does here is speed up the reaction. So answer here is C, catalyze the decomposition reaction. Question 32. If the student misread his thermometer and recorded a temperature that was lower than the actual room temperature, his calculated value of the ideal gas constant would be. All right, so let's take a look here. He measures PV and N correctly, but T he measures to be lower. Is that what it said?
Yes.
Yeah, so T he measures to be lower, and he plugs in that lower value here. Now, if T is lower, what's going to happen to R?
R is going to go higher.
Yeah, exactly. When he calculates for R is going to be too high. He's going to check that, compare that with the book, and his calculated value is going to be too high. So answer is going to be A, higher than the literature value.
Very nice.
Question 33. The oxygen gas in this experiment can be considered an ideal gas because, now when they ask you this question, you want to just think basic science. And in basic science, we know that a gas starts to deviate from ideal behavior when those molecules get close together. So what brings molecules close together?
High pressure?
Two things. Pressure, we squeeze them close together, and then the other thing is we cool it off, right? The low temperature allows them to settle in and get close together. Those two things, when the molecules get close together, those two things then, high pressure, low temperature, cause ideal deviation. Now this question is funny because it says we can consider it an ideal gas because, so we can consider it an ideal gas because it must be at low pressure and high temperature. And so answer here is D. The experiment is not done at low temperatures and high pressures. Question 34. If the same experiment were performed using ethanol, and they give me 0.79 grams per milliliter in place of water, and the same amount of potassium chlorate were reacted, how would the amount of ethanol displaced in the second experiment compare to the amount of water displaced in the first experiment? Something you have to know here about water. And what is that?
Its density is 1.
Exactly. Its density is 1 gram per milliliter. So water has a greater density than ethanol. And what does that mean in terms of how much fluid would be displaced? Remember, the gas is displacing its volume in fluid. So whether this is water or whether it's ethanol, the same volume will come out into the beaker, right? Because a gas displaces its volume. Once it comes out in the beaker, though, it'll have a different weight. Water is 1 gram per milliliter, and the ethanol is 0.79 grams per milliliter. So if we had 100 milliliters, we'd have 100 grams of water, or if we had 100 milliliters of ethanol, we'd have 79 grams. So we know the ethanol would weigh less. So answer choice then is D. The mass of ethanol displaced would be less, but the volume would be the same.
Oh, here's that pen. All right, we're ready to do passage 6 in the physical sciences section. Starting with question 35. It's a half-life problem with a little bit of a twist. It says a sealed container holds a 0.2 gram sample of pure polonium. So we got a 0.2 gram sample of polonium. And what happens is, after 277 days, the question asks, what is the composition of the sample? So of course what's happening is polonium is decaying into something else. So there's a decay reaction going on. It says in the passage that it emits alpha particles with an energy of blah, blah, blah. So it becomes some unknown. If we check the periodic table, polonium will have a mass of 210 and an atomic number of 84. So our unknown is the polonium nucleus minus an alpha particle, a 4,2. That would make our unknown, the mass would be 206, and the atomic number of our unknown would be 82. So what's going on is we've got a half-life problem, and it says also about polonium in the middle of in the front of the second paragraph that the half-life of polonium is 138 days. In other words, we're doing 2 half-lives. 138 days, we'd have 0.1 grams of polonium, and after another 138 days, John, how many grams of polonium would we have left?
0.5.
That would be
0.05.
0.05. So we
Right.
have 0.05 grams of polonium left after 2 half-lives. But the twist to this particular question is we also have something else. In other words, as polonium decays, X, our unknown, builds up. After, presumably, we'd have 0 of X initially. After 1 half-life, we have 0.1 of this. And because this mass is so small relative to this mass, we have 0.1 grams of this. After 2 half-lives, we have 0.05, so we've added another 0.05, or subtracted another 0.05. We must have added it again to this mass. We must have 0.15 grams of our unknown. Let's find the answer choice that says that. That would be B, 0.05 grams of polonium and 0.15 grams of, and then they identify our unknown, which you could identify by checking the periodic table for element number 82, finding lead.
Right. Now notice here you did not have to identify the unknown.
Right.
Right? If you looked at the answer choices and you knew the half-life, you'd say 277 days, 138 is then, that's a half-life. That's 2 half-lives. 277 days is 2 half-lives. So we're going to have 2 half-lives, so we get that. We know we end up with 0.05. The trick here then is C looks like a good answer.
Right.
Except it says polonium only. And we know something's got to happen, right? There's got to be, that mass doesn't disappear. It's got to go somewhere. And it goes to the unknown. And of course, it should add up, the total mass should add up to 0.2. So choice B then is our best answer.
Great. Question 36. Which of the following is a true statement concerning a comet passing near the sun? Assume the mass of the comet is negligible when compared to that of the sun and ignore any effect of the planets and any mass loss by the comet. In the last paragraph, it says, if a comet's path does not happen to bring it near to the sun, it will only be deflected slightly. If the path ventures near the sun, however, the comet may whip around the sun, perhaps even returning in nearly the direction from which it came. So let's draw a diagram, because I'm not entirely sure what's going on. We're going to go to the draw diagram model, right? And here we have the comet moving through space, and we'll indicate its direction in this way towards the sun. And here's the sun. And what's going on is it never actually contacts the sun. It says in the passage that it can be whipped around the sun like this. And what we've got is we've got an initial velocity of the comet towards and a final velocity of the comet away from the sun. So we've got 2 different velocity vectors for the comet, meaning we've got 2 different momentums. So momentum in this case cannot be conserved. So let's eliminate then answer choices A and B, because those both say that momentum would be conserved or nearly conserved. So now the question is, which is better? Well, again, we don't have a collision, but if we thought about it, this is probably closer to an elastic collision, because it's going to, whatever velocity this is going to be reflected in this velocity. In other words, the size or the magnitude of this velocity will be the size or magnitude of this velocity, so it's very close to an elastic collision. C says the mechanical energy of the comet is nearly conserved because the interaction with the sun is similar to an elastic collision, which is exactly what we're saying. And you need to remember that mechanical energy, in elastic collisions, mechanical energy is conserved.
Yeah, the important point is here, don't try and make sense of C and D. I mean, who cares if this is like an elastic or an inelastic collision? You don't have to know. Look at the answer choices. Mechanical energy is conserved when? In an elastic collision, so C must be the correct answer because D says inelastic. If you try and analyze this to figure out how it's like a collision, you're wasting your time.
Good. Question 37. Suppose the alpha particle felt no force as it traveled through the foil. Which of the following would describe its motion? John, if there's no force, what does that mean?
No force means no acceleration.
No acceleration. Let's find the answer choice that says that. Oh, I'm looking at D. It says would travel at a constant velocity. Of course, an acceleration is a change in velocity over time. If there's no acceleration, velocity is constant. 37 is D. Question 38. Before conducting his experiment, Rutherford believed atoms were composed of a uniform positive jelly in which electrons were embedded like chocolate chips in a cookie. Makes me hungry. If this were an accurate structure for the atom, what would the result of Rutherford's gold foil experiment likely have been? Right? And then there's a note at the bottom. It says the alpha particle was known to be much more massive than an electron. So, in fact, let's sort of look at Rutherford's experiment and use the analogy made in the question. What we've got here in our figure is we've got a gold foil and we're going to fire alpha particles, very large alpha particles relative to the electrons in there. We're going to fire them at the gold foil. And if, in fact, this is just a chocolate chip cookie with a couple of electrons embedded in it, those alpha particles are going to go right through and smack up against the receiving apparatus on the other end. I kind of think of it, let's draw a chocolate chip cookie here with a bunch of electrons or chocolate chips in it. And now let's take an alpha particle, or better yet, let's take a bullet, and we're going to fire that bullet at the chocolate chip cookie. So here's the bullet. And of course, we all know the answer to this question. This is nice, one of those nice, soft, chewy chocolate chip cookies. We fire a bullet at it. The bullet's going right through that chocolate chip cookie, not going to be affected by anything. Hits the receiving screen at the end. Everything makes sense. But that's not, in fact, what happened in Rutherford's experiment. What happened in Rutherford's experiment was some of these bullets hit and were deflected, or some actually bounced right back towards the fluorescent screen.
So what they found out is it's like a big rock in the middle of that chocolate chip cookie, and that's the nucleus.
Yeah.
I got it.
That's what Rutherford's experiment demonstrates. Let's find the right answer to this question. A says none of the alpha particles would have been deflected by a large A is the right answer. None of the alpha particles would have been deflected by a large amount. They would have gone straight through the cookie, nothing would have happened, right? B says all of the particles would have been deflected by a large amount. And the problem is there is all of the particles. Obviously all, I like that answer choice, or I like to spend just a half second on that answer choice, because some students will go for it. That can't be it, because the word all is really a bad word in that case.
Well, and we know from the gun shooting through the cookie, none of those bullets are deflected. The alpha particle is 7,200 times heavier than an electron. It's not going to be deflected. But if it hits a nucleus, it's going to be deflected. And that's what Rutherford didn't know. He didn't know there was a nucleus in there.
Right.
So none of the particles are going to be deflected.
Good. Let's go on. Question 39. When the alpha particle is emitted by the polonium atom, what energy transfer is taking place? So when the alpha particle here is being emitted by polonium. So before the alpha particle is emitted, we have a sort of a polonium atom sitting there minding its own business, doing nothing. All it has is mass. And then all of a sudden, poof, out comes an alpha particle with a velocity. So what's going on? We must start with mass, and we're going to something else. Let's look at our answer choices. Only answer choice D says mass to something. That would be mass to kinetic energy. When the alpha particle is emitted, it's emitted with a velocity. Obviously, if it's a velocity and it has a mass, it's going to have a kinetic energy. We have an energy conversion from mass to kinetic.
And that's always going to be true with the nuclear decay. It's going to be mass energy to kinetic energy.
Absolutely. Question 40. Which of the following describes what happens in the experiment when a flash appears on the fluorescent screen? Well, here's the fluorescent screen. John, what is exactly going on when we look at this? What happens when there should be gamma rays coming out or something. When a flash occurs on the fluorescent screen, something must be hitting the fluorescent screen. And the question is, what is hitting it? Well, we're shooting alpha particles out here, and the whole passage, really, the main idea of this passage is the alpha particles are going in different directions.
Right, they're measuring where the alpha particles are hitting based on that flash, and then the flash, so it's got to be answer C or D. An alpha particle is absorbed. And is its energy transferred into photons or electrons?
Well, electrons.
It's a flash.
Yeah, it's a flash. So
it's got to be photons. It's got to be light.
Good. Best answer for 40 is C.
Jordon, I'm so glad you came over on Boys Night Out. It just gets so lonely.
It does get lonely, doesn't it?
It does. You know, this MCAT stuff the boys do, they're just, I don't think it's so difficult.
No. Should we have it one?
Let's try.
Okay. Do you mind if I do it?
Oh, please, please.
Okay. We'll look at passage 7 then. Passage 7. Question 41 says, assuming 100% ionic character and an R value of 2.027 angstroms, what is the calculated dipole for lithium chloride? Well, let's see. They give us a formula in the passage. Where is it? Oh, here it is, equation 2, yes. It says U, which they describe as the percent dipole character.
And that's what they're asking for.
Is exactly. So let's plug in some values, shall we? We've got 0.2082. Wasn't that wonderful? What a great number.
And they give us R, Jordon. This is easy.
Read it to me.
Easy. It's 2.0 0.27.
Excellent.
Oh, it's so easy.
And then it's 100% ionic character, which of course would be a 1, so we'll multiply the entire fraction here by 1.
It says right in the passage, 100% ionic characters, 1.
1.
1.
2 over 0.2. This is 10. Oh my goodness.
We have an answer?
41 is D.
Okay.
D for 41.
D.
42. From the information in Table 1, it can be predicted that HBr will have a percent ionic character of approximately... Well, let's look at Table 1, shall we, dearest? It's Table 1.
You know, a Br is a halogen, I believe. I heard the boys say it once. And we have a halogen here and a halogen here.
Okay.
And Br seems... Oh, good, good. Br is between Cl and I, so I think it should be somewhere in the middle.
Okay, let's find that.
Let's take a look. HCl, and we're looking for, what are we looking for again, dear?
We're looking for percent ionic character.
Percent ionic character. Okay.
And we're looking for a value that will appear somewhere between where HI's does and where HCl's does.
Between a 6 and an 8. Let's see if we have a value.
And an 18. 18, dearest.
18, thank you.
Answer choice C says a 12. 12!
Another one? Really, this is just... It's
Too
really
easy.
not that
yes,
tough.
boys brag
Those
about
boys.
how difficult this is. 43. If mu represents the dipole moment of each CCl bond in CCl4, what is the dipole moment of CCl4? Now let me think. Can I draw a CCl4?
CCl. I believe I heard Jordan call that carbon tetrachloride once.
Oh, carbon tetrachloride. Let's see, we have a C.
Four bonds.
Okay. Right.
Oh, it looks very good, very good. Oh, yes. And this is three-dimensional, so it would be a tetrahedral.
Tetrahedral.
And the dipoles, I think they would cancel out.
Each one of these bonds is polar. And they're all, because they're all pointing in different directions, they're going to cancel each other out. The net is 0.
0? Oh, I love those zeros.
Yes,
okay,
wonderful.
A. 43 is A then.
A. 44. The forces in an intramolecular bond are electrostatic. Which of the following hydrogen halides has the greatest bond energy?
Oh, let me
dear.
do this one, Jordine.
Okay.
Okay. I think they mention electrostatic forces, and electrostatic forces, as we know, have something to do with dipole moments. And if we look, we have the halogens again.
Okay.
Fluorine has the highest electronegativity, which means it's going to have the strongest bond between the hydrogen and the fluorine, the greatest dipole moment.
Oh.
The strongest bond will require the most energy to break it apart. Does that make sense to you?
Sort of.
Okay. So that would leave us to answer choice A.
A must be
A
right.
is correct for 44.
Oh,
This is so easy.
Excellent. Well,
Okay.
that brings us to the end of the passage.
Oh, well.
Oh,
so,
dear.
I guess we'll go out.
Tiddly on. Ta-ta. Now, how do I look, dearest?
Oh, you look beautiful.
Yes. Do you like the glasses?
I love them. Okay, passage 8. Passage 8, question number 45. At very high temperatures, reaction 1 will most likely be, well, if we take a look at reaction 1, and we look at the answer choices, they're asking about spontaneous and then exothermic or endothermic. We can see right away that reaction 1 is exothermic, and the temperature change is not going to change that. So we know it's exothermic, so we know it's either got to be answer A or C. Now the question is it spontaneous or non-spontaneous? If we take a look here at the reaction, these are gas molecules, and here we have 1.5 gas molecules on the reactant side, and the product side we have 1 gas molecule. What does that mean about entropy?
It means it's decreasing. We're going from more gas molecules to fewer.
Exactly, so we have a negative entropy. So if we take a look then, we've got a negative entropy and a negative enthalpy, and we look at this equation, delta G equals delta H minus T delta S. Delta S is negative, delta H is negative. If delta S is negative, minus a negative number is a positive. So we could have either, this whole thing is going to be positive, so we could either end up with a delta G of positive or negative. And what does it depend upon?
It depends upon the size of the temperature or the value of the temperature.
Exactly, the temperature component. If the temperature is high, some big number times delta S, that's going to make this component very high. So this whole component, then a high negative minus a high negative is going to be positive. So at a high positive value, we have a delta G that's positive, and that's going to be
non-spontaneous.
Non-spontaneous. So answer choice C, non-spontaneous and exothermic. Question 46. The enthalpy of formation of liquid water is negative 285 kilojoules per mole. According to the student's experiment, it can be determined that the enthalpy of formation of MgO solid is, all right, if we take a look at this, they gave us a hint in the passage, the enthalpy of formation of water. Enthalpy of formation of any compound is taking its elements and forming that compound. So for water, we have H2 plus 1/2 O2 goes to H2O. And they told us that is a negative, a delta H that's negative 285. Okay? That's my enthalpy of formation of water. Now, I want to form MgOS, solid. So I want to determine the enthalpy of formation of MgOS solid. So over here I need my MgO solid. Now my enthalpy of formation equation for that is going to be, again from the elements, Mg solid, plus 1/2 O2. So I want to get that equation. I'm starting from here. I'm going to use some of the equations or some of the reactions they gave me in the passage. So the first thing is I'm going to look at this. I want MgO solid on the product side. I look at my reactions. Where do I find MgO solid? Here's reaction 3 and 4. I see that I have MgO solid here on the reactant side, so I'm going to flip that. And I'll go ahead and write that out then. Then I've got H2O plus Mg2 plus goes to 2H plus MgO. And since I flipped it, I'm going to change the sign here. And my delta H then is a positive 115. Okay, so I've got my MgO solid here and MgO solid here. All right, notice my H2O, I made one, and then I used that up, so I can get rid of that. Now, I have my 1/2 O here and my 1/2 O here. So what do I still need here? I need to get rid of the H2, I need to get rid of the 2H plus, and I need to make an MgS on the reactant side. I'll look for another equation. Here's one. Let me go ahead and write that in. Mg solid plus 2H plus goes to H2 gas plus Mg2 plus, and then that delta H is negative 420. Let's see what that did for me. I had my reactant, H2, I used it up, and then I made it again, so that cancels. My Mg solid, I can bring down here, okay? I'm going to make an Mg2 plus, and then I'm going to use it up over here. I'm going to use up 2H plus, and I'm going to make it again here. I'm all set. I've got my reaction. So now I can just add these up, and I have negative 285 and a negative 420. That's about a negative 700 minus another 100. So I'm a little bit under a negative 600. So if we take a look here, I have answer choice C, negative 590. Question 47. Which of the following describes reaction 3 at STP? All right. I've written up reaction 3. Right here is my reaction 3 at STP. Now reaction 3 at STP, well, first thing I'm going to do is look at my answer choices. They're talking again about exothermic and spontaneous. Reaction 3 then is exothermic, so I know it's got to be either answer choice A or C. And then I have to look at the gas molecules again. I have gas molecules here and no gas molecules here. What does that mean?
That means I've got more entropy in the products than in the reactants.
Exactly. So I have a positive entropy and a negative enthalpy. And again, if I go back to my equation, delta G equals delta H minus T delta S. If I have a positive entropy and a negative enthalpy minus a positive, this has to be
a negative.
A negative. So it's got to be a spontaneous reaction at any temperature. Answer choice A.
A.
Question 48. Given that delta HF for H plus aqueous is 0, what is a delta HF of Mg plus? Okay, again, we're going to do the same thing we did in question 46. We want the delta HF of Mg2 plus. So we're going to form Mg2 plus. And we form that from its elements. So from Mg solid, we're going to get rid of electrons and make my Mg2 plus. And they want to know the enthalpy of formation for that. They give me the enthalpy of formation for H plus as 0. So 1/2 H2 goes to 1 H plus, and that enthalpy of formation equals 0. Okay. So how do we go from here to here? If we take a look at reaction 4 down here, we see that we're forming Mg2 plus. So that's the reaction we're going to look for. Oh, you know what? It's probably going to be easier for me to do this one. I'm going to notice H2 here and H2 here. It's going to be easier. So I think I'll just use reaction 3, Mg2 plus, H2, and Mg solid plus 2H plus. And if I take a look at that, well, that's going to be my delta H3 of negative 420. Okay. Now, here I'm going to go ahead and multiply this through by 2. And when I multiply this by 2, I have to multiply this by 2, but it's 0. So I'm just fine. Right? And then I use up 2 H2s, and I make...
Well,
I'm sorry, I multiplied this.
I
made a mistake when I multiplied. So this is just 1, because 2 times 1/2. So I use up an H2, and I make an H2. I create 2 H pluses. I use up 2 H pluses. I've got left over this one and this one, which is the reaction I'm looking for. Negative 420 should be my answer. And that's answer choice C on number 48. Question 49. Why can Hess's law be applied to reactions 1 and 2? Well, the reason we can apply Hess's law is we can apply Hess's law when we have a state function. And thermodynamic properties, for the most part, are state functions. So certainly enthalpy and entropy are state functions. So we can apply Hess's law. So answer choice for 49 then is D. Now, just to clarify, a state function means that it is pathway independent. We start with certain things and we end with certain things. The path we took to get there didn't matter. That's why I can add these reactions the way I did. They didn't necessarily happen in that order, but the path doesn't matter. It matters what I started with, which is here, and what I ended with. And that's a state function. Okay, we're on the second set of freestanding questions in the physics section. Question number 50. Nitrosyl chloride is formed by the following reaction. I've written the reaction up here. In a student experiment, this reaction is allowed to reach equilibrium in a sealed 22.4 liter container at 0 degrees Celsius. The initial pressure is 10 atmospheres. If a student adds 2 moles of NO gas to the sealed container and allows the reaction to reach equilibrium, the final pressure will be... All right, so we have a sealed container. We're going to add 2 moles of NO gas, so that's going to tend to push the reaction in that direction. Now, it's a 22.4 liter container, and it has 10 atmospheres. So how many moles of gas must we have?
There's got to be 10 moles already.
Exactly, because each mole gives me 1 atmosphere of gas. So we have 10 moles. Now, when we add 2 more moles, we'd expect the pressure to go up to, if nothing else happened,
12 atmospheres.
To 12 atmospheres, because we'd have 12 moles of gas in 22.4 liters. However, something does happen. The reaction moves in this direction. We have 3 gas molecules on this side and 2 gas molecules on this side. So if the reaction moves this way, I'm getting fewer gas molecules. So let's add the 2 moles of gas here, and that brings us from 10 atmospheres to 12, but then the reaction moves towards equilibrium and reduces the number of molecules. The question is, will it reduce back down to 10 atmospheres?
No.
It will not. The Le Chatelier's principle says that the reaction wants to compensate for the stress, but it can't totally compensate. It doesn't totally compensate. So so what's going to happen is the pressure is going to be somewhere between 10 and 12. Best answer here is C, less than 12 atmospheres, because Le Chatelier's principle predicts that the equilibrium will shift to the right. Question 51. Oxygen difluoride is produced when fluorine gas is bubbled into a dilute solution of sodium hydroxide. What is the hybridization of oxygen in oxygen difluoride? Now, for this question, what does oxygen difluoride look like?
Well, it's going to be OF2. It's going to look a lot like water.
A lot like water. You need to know that fluorine's a halogen, and halogens are monovalent for the most part. They can make more than one bond, but typically you would assume halogens will make one bond. And fluorine always makes one bond. It's too small to make more than one bond. So oxygen then is going to have its two lone pairs of electrons. Looks just like water. sp3, answer choice C. 52. 100 milliliters of 0.1 molar sodium chloride is mixed in a container with 100 milliliters of 0.1 molar sodium sulfate. What is the molarity of sodium in the final solution? All right, so let's take a look. We have sodium chloride. Just erase our fluorine there. So we have sodium chloride, and we have how many?
We have 0.01 molar sodium chloride. And
0.01 molar, okay.
And we have 100 mils of it.
And 100 mils, okay. So to find out how many moles of sodium chloride that we have, by the way, each sodium chloride is going to break into one sodium and one chloride. To find out how many moles, we're going to multiply molarity times liters. We'll change this to liters, which will be 0.1. So 0.01 times 0.1 gives me 10 to the negative third moles of sodium ions.
Excellent.
Okay. Then we have sodium sulfate. And this is going to break up into sulfate ion and 2 sodium ions. And we have 0.01 molar sodium sulfate. We have 100 milliliters.
Yes.
We're going to do the same thing, and we get 10 to the negative third. But remember, there are 2. That 10 to the negative third is how many sodium sulfates we have. And we have 2 sodiums for every sodium sulfate. So we're going to have 2 times 10 to the negative third moles of sodium from the sodium sulfate. Now to find the molarity, and that's what the question is asking for, we're going to add our number of moles. This is 2 and this is 1 more. So we have 3 times 10 to the negative third total moles of sodium.
From both solutions combined.
Both combined. And then we have to divide by the total volume, which is going to be 200 milliliters, right? And actually, let's change that to liters. So 0.2. So we have...
And John, I just want to point out, you could, at this point, you set the problem up very, very well. You have 2 choices. You could continue, do all the math and get the problem, or you could just look at your answer choices, and 3 over 2, obviously you're going to have a 0.15 or a 1.5 in there. So I would immediately go to answer choice B and move on.
Great. Yeah, you're saying not worried about the decimal point.
Right.
Because you can see 3 over 2 is going to be some 0.15 or 0.015.
Right.
Good. So answer choice there is B. Question 53. If the voltage across the capacitor is doubled, the net force on the dipole will. All right, we have a diagram for this. We've got a capacitor here. That means one side is positive and the other side is negative.
It's upside down.
It doesn't really matter which side is positive and negative. And it doesn't really make any difference if it's upside down either, does it?
True.
Okay, so let's say this side's positive, this side's negative. If this side's positive, it will repel the positive end of the dipole, and this negative side will attract it. So there'll be a force, EQ, in that direction. Because recall that the force on a charge inside an electric field is equal to E times Q, the electric field times the charge. So force EQ this way. On this end of the dipole, there's an equal and opposite charge. That's the definition of a dipole, separated equal and opposite charges. The equal and opposite charge will be attracted to the positive and repelled by the negative with a force EQ, F equals EQ. So I have EQ this way, EQ this way. The net force is 0. The question asks me, the net force on the dipole will, notice it didn't matter what the voltage was. The net force would stay 0. So answer choice B, it'll remain the same. It'll stay 0. Question 54. The hydraulic lift below lifts a 1 kilogram mass 5 centimeters. If the cross-sectional area of the piston 1 is 25 square centimeters, the cross-sectional area of piston 2 is 100 square centimeters, what is the approximate work done by force F?
Whoa, this looks like a really hard problem. I mean, I don't even remember any hydraulics.
It looks like a tough problem. It looks like we have to figure out this hydraulic machine. But in reality, remember, always in an MCAT question, look for the easy way to answer it.
All right.
Whenever you see a machine and they talk about work, we're going to answer it with energy, not with vectors. They've kind of misled us because they ask, what is the work done by the force? It doesn't matter what the work, if it's by the force or by what force. The work done is always going to be the same on a machine, on an ideal machine. The easiest way to answer this is ignore the machine part and look at what's going to happen. I have a 1 kilogram block that's going to be lifted 5 centimeters. The work done will be the change in potential energy. And the change in potential energy is going to be m times g times h. In this case, m is going to be 1, g is 10, and h is, in centimeters, 0.05. So the total work done is a half a joule. Answer choice A.
So that wasn't hard at all.
Not too
Had
tough.
nothing to do with hydraulics. This was clearly an example of a misdirection type question. They want you to start following a primrose path and be confused. Don't do it. Just do it as John did.
Are you ready for the fishing trip this weekend?
Oh yeah, we're going up to Lake Minitata.
That's right. You know what? I invited Jon and Jordan over, so maybe we ought to
Get
move
the furniture out of the way, right?
You know how they are. All right. Ready? 1, 2, 3.
You start?
Argonga. We wait for Jorga. We do passage 9, test 1. There's Jorga now. Jorga, not too smart. No learned door yet. I learned last week. Oh, Jorga. Okay, I got it. Door easy. You not learned door yet. You need learn door.
Or not on MCAT.
Okay, passage.
What are we doing?
Passage 9. Question. Hold on. I not see. Hold on. Better. Okay. What is the approximate wavelength of an S wave? S. Without teeth. Easier. What is approximate wavelength of S wave with a period of 2 seconds? 2 seconds.
2 seconds.
2 seconds. Okay. We need formula. Formula. I put teeth here. You know where.
Okay.
Okay.
V
V
equals F lambda.
F lambda. We need period.
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 One period.
Period. F. I know. Equal 1 over T.
Period.
Yeah. Substitution. Substitution. V equal. No F. Lambda over T.
And over T.
Plug and chug.
Question say, period. 2 seconds.
2 seconds. 2.
And passage, it's a velocity 4 kilometers per second.
That velocity.
4K.
4 kilometers per second equal lambda over 2. Algebra no invented yet. We in trouble. Wait. 2 times both sides. 8 equals wavelength. 8 kilometers.
Answer choice C.
Answer. Okay. Oh, good. Very good.
I got it. Question 56.
56, okay. I read without glasses. I read better. One type of wave created by an earthquake is essentially a low-frequency sound wave traveling through the earth. Which of the following has characteristics most similar to those of sound wave?
Sound wave. Let's look.
You can't see sound wave, stupid. Stupid! Okay, sound wave, longitudinal wave. Sound wave, passage say, P waves, which are longitudinal waves. P waves.
Longitudinal.
Sound waves, longitudinal.
First paragraph.
B.
Last answer. Next question.
Next. 57. A seismic station receives waves from an earthquake. Earthquake! Shake! Okay. 200 kilometers away. You draw a seismic station.
What seismic station?
Good. Earthquake. Seismic station. Seismic station. You learn how to hold pencil yet, either. Okay. 200 kilometers. 200. Passage say, P wave, 7 kilometers per second.
P wave, 7.
S wave, 4 kilometers per second.
4.
We need formula. Questions say, which of the following is true? Okay. So formula, how long? They talk about how long to travel. P wave, here to here. S wave, here to here. Formula.
Okay. D.
Velocity equals distance times time. Okay. Distance, 200. Velocity, 7 times time. 7.
Wait. D equals VT.
Stupid! Stupid! I knew that. V T equals D. Very stupid, you. Okay. V 7 T equals 200. T equals 200 over 7.
For P wave.
For P wave, approximately. Let's say 30. 30, good number, round
30
number.
seconds, P wave.
Round
here,
number.
Here, 30.
Yeah. Okay. S wave. 4 T equals 200. T equal 200 over 4 equal 50.
Second.
30. 50.
This one, get there first.
P wave, 20 seconds faster.
20 seconds.
Okay, we find answer.
D. Say, first S wave arrived about 20 seconds after first P wave.
D, right answer.
D.
57, D. Number 58. Okay. A building in an earthquake may sway back and forth with gradually increasing amplitude until a collapse finally occurs. This is an example of, okay, building an earthquake. Building sway back and forth. Here building. Earthquake, waves strike here. Building sway. Another earthquake here. Sway farther. Another earthquake here. Boom. Sway farther until boom. All gone. Building gone. Okay, bad. Okay. Only wave must strike just right time, called resonance frequency. You understand?
No.
Okay, it's okay. Okay, resonance. Choice C.
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 P. Okay,
Relax. Okay, you relax. Choice A, no good. I need to explain why. Okay, choice A. Choice A, destructive interference. Wave like this. Wave like this. We add waves. They destroy each other. This high, this low. We add them. Line. Destructive interference.
Oh, this why no. A not good for 50.
No
A.
hurt building. No hurt building. No. Need to brush my teeth. Okay. 59. 59. The ratio of energy involved in the largest recorded earthquake to the energy involved in one of Richter magnitude 5.0 is... Okay, passage, give hint. The Richter scale is a logarithmic scale, similar to pH scale.
Oh, logarithmic. Base 10 logarithmic.
Base 10, yes, each point 10 times, each point. Passage also say the largest recorded Richter magnitude, approximately 9.0.
Oh, 9.
9. 4 points bigger than 5.
9 is 5 equals 4.